Hello everyone, welcome to lecture 4 of week 3 of the course Simulation of Modern Power Systems. This lecture or discussion is going to be the last one on the module Power Flow Analysis, and in this discussion we will understand a common technique known as backward and forward, specifically for distribution network power flow analysis. The reasons why the previous techniques of power flow such as Gauss-Seidel, Newton-Raphson, fast decoupled method, why these techniques don't work well for distribution networks, the same would also be discussed. And towards the end of this discussion, we'll also understand an example of a typical distribution network whose power flow, if it is to be obtained by Newton-Raphson technique, then the method would fail or have a hard time getting a converse solution, whereas this forward-backward technique will be able to give us the corresponding voltage phasors of all buses in the considered radial distribution network. The last lecture was on another special technique of power flow known as DC power flow, which is very useful in contingency analysis, which we will discuss as part of the next discussion. And the reason why DC power flow is so used or so popular in contingency analysis is because of the fact that DC power flow is a linear non-iterative technique of being able to provide voltage phase angles and real power flows of in a given power network for known real power injections. Being linear and non-iterative, it provides quick estimates of voltage phase angles, which are very useful in the contingency analysis exercise, where as the system operator one has to screen, filter, process several such contingencies for a practical network. And if one were to do actual AC power flow for each of these contingencies, then probably the time required would be very, very high, and by the time all AC power flows provide the impact of each contingency in the power network, the time of event of occurrence of contingency would have come in and the system would have already got affected. Getting to know this previous states or earlier analysis will help the operator take proper action plan, I would say control action plan, so that the system security is not at stake. We'll discuss more about this when we discuss the next module. So, as I was discussing in the opening discussion, that conventional power flow methods generally cannot be used for power flow analysis of distribution systems. The first and primary most reason for this is that unlike high voltage transmission systems, which are by system design on operation are balanced systems, distribution systems on the other hand are highly unbalanced. It is also possible that this unbalancing is not just because of unbalanced loads, but also because of the fact that not every line section of the distribution network will have all the phases present in it. It may happen that across a radial feeder, only one phase is protruding out to the next section, while the previous feeder had only the remaining phases considered. So, it's not just because that we have unbalanced loads, which are also true for distribution network, the network itself is also unbalanced. And if this is the case, then how do we apply the balanced transmission network power flow methods that we have discussed so far is where the problem is. So, essentially we have to understand a method which provides not just single phase power flow voltages, but three phase power flow, which would provide three phase voltage phasors for all buses or nodes in the considered distribution network. This is a practical aspect or an issue. The mathematical part is that usually distribution systems, their voltage levels are low, as a result of which their corresponding line reactances are low, and the line resistance doesn't change. In fact, one can also say that if I were to use the same transmission line conductor or cable in the distribution network, Because of low operating voltages, the line will exhibit lower reactance, as a result of which the same transmission line conductor will exhibit high R by X ratio when it is used for distribution network. This is a theoretical discussion. Practically, transmission line cables and distribution line cables have different designings because of different levels of operating voltages. So if high R by X ratio is the case, because lower voltages lead to lesser reactance, the reasonings of how this X depends on the operating voltage, it has its root in the transmission line parameter evaluation module, which is often discussed in the undergraduate third year level courses. So those of you who want to understand the relationship or linkage between X and the voltage level, please revise that particular aspect of transmission line parameter evaluation. And also, as I mentioned, distribution networks are mostly radial with single in-feed or one substation source systems. Systems with multiple sources can be ultimately analyzed as radial systems, wherein we usually have one slack or source bus, and there are many PQ buses. Often there are no PV buses present, as long as there is a distributed generator present in the distribution system somewhere. So the mathematical problem with these two reasons is that the Jacobian matrix, which is essential in Newton-Raphson method, if one were to understand or see its elements, specifically for the case when voltage phasors are in polar coordinates, then these elements, if one were to re-see and evaluate, it has certain diagonal terms, which I would say like diagonal, and then certain off-diagonal terms. When the lines have high R by X ratio or the system becomes radial, the off-diagonal terms in the Jacobian tend to dominate the diagonal terms, as a result of which the Jacobian matrix starts becoming ill-conditioned or its factorization becomes difficult. That is a mathematical reasoning. The other reasoning one can also understand is that in fast decoupled method, we understood that real power and voltage phase angle have strong coupling. Reactive power and voltage magnitude have strong coupling. This is again because this was there for fast decoupled power flow. This was again because of the case that transmission systems have very low R by X ratio, as a result of which, if one were to see the Jacobian elements, the diagonal terms, then they are very, very dominant compared to the off-diagonal terms, and hence this coupling holds true for transmission system. This coupling is not at all applicable for distribution systems because of high R by X ratio and high radial nature. So coupling itself, behavior changes. In fact, if I were to summarize or state that both real and reactive power, they have correlation with voltage phase angle as well as magnitude. The quantum of their significance or relationship varies for different systems based on their operating voltage and R by X ratios. So as I mentioned earlier, the decoupling aspect is no more valid. P and theta are not just only decoupled from Q and V. All two elements are dependent on the other two. Jacobian starts becoming ill-conditioned or rag deficient, and hence one has to also understand what can be done so that the distribution network power flow can be done. So typically, as I mentioned, every line section is a three-phase section in distribution network. If all the three phases are present, then all the three have to be modeled as nominal pi model of the corresponding distribution line. And similarly, the load also needs to be considered in a three-phase manner. So we, instead of just having one phase, which was commonly true in the case of balanced power flow, now we have to have all the three loads considered, where PA, PB, PC, and likewise QA, QB, QC, they need not be equal to each other. What we would understand is a very specific technique. There are variants of techniques for distribution system power flow. For our discussion, we will focus on one preliminary basic technique known as backward and forward method. Then the reason behind this name backward and forward would become clear when I go deep into the corresponding discussion. Also, the distribution network that I would consider for explaining this method would be for a single phase network, so that the corresponding explanation and discussion becomes easier. However, the same method can also be applied when we have actual three-phase distribution network. The diagram that I have shown here is a simple single phase distribution network that I have considered for the sake of our discussion. Source 1, which is the voltage bus number 1, this is considered as a source bus whose voltage magnitude is known, and it also acts as reference for all voltage phase angles. So depending on the transformer tap position of the distribution network transformer, which is basically the substation transformer, depending on that voltage and the per unit voltage reference that we have chosen, it is often the case that V1 voltage can be chosen as 1 at an angle 0 degree or radian in per unit. And the network that I have considered, the numbers encircled in the square boxes are the bus numbers, whereas the numbers sort of within the simple brackets are the branch or the line numbers. So what does this forward-backward method or backward-forward method do? It starts with an initial choice of voltages, preferably flat start, the way it was done for the transmission network power flow analysis. And based on this, the method starts with the farthest end buses, such as in this case, we would start the method by doing something on bus number 7, 8, 10 and 9. Using this, we try to find the corresponding currents that would be flowing on these lines in order to feed the load or injection at the far end buses. So using this, we try to find the current at the farthest end node, use that current to find the corresponding branch current. Once we know the branch current, the same exercise is applied to bus number 5. Using this current and the outgoing currents, we are able to find the current on branch number 4, and we keep on doing so till we reach branch number 1 current, which is based on the voltage source that has been chosen here. So once we get to know the currents from the far end to the source end, it's now time to update the voltages based on the currents that we have obtained. So we do the traversing or finding currents from far end nodes to the source end node is the backward phase. The forward phase would be updating the voltages based on the currents that have been obtained and trying to update the voltages now, voltage phasors now of the buses, so that there is a balance between the branch currents and the bus voltages. That is the essence or basic behind what the backward forward method does. So from the source end, we update the node end voltages, as I mentioned, with the resistant currents in the forward method, and this goes on till there is a convergence reached. The convergence could be in terms of change in the voltage phasors or the change or the maximum absolute error that exists in the bus injections. We will come to the convergence part a bit when we discuss the corresponding example. For time being, I will focus or start with bus number 10 here. It's actually wrongly placed here. It's the focus part is bus number 6, 10 and 9. I'll start my discussion with bus number 10. Whatever is being discussed for bus number 10, the same would be true for bus 7, 8 and 9 and for the previous backward buses. So suppose at bus number 10, I know what is the demand, complex demand, and if at all there is a generator present at bus number 10, then I also know its specification, provided that it is a PV bus. Usually this generator will not be present at the far end buses. So the demands are known. If at all generation is present, its generation is known. If it is a PV bus, then the Q value has to be evaluated the way it was done for Newton-Raphson or Gauss-Seidel method, that is at the latest voltages, find the injections, see if it is within the limit. If it is within the limit, fine. If it is not within the limit, that means it has to be set at the corresponding maximum or minimum Q limit, whichever it is trying to violate, and then voltage becomes a free variable. If Q is within the limit, then the voltage magnitude doesn't change. The same logic would be true for SG10 also. So assuming that we know these demands and generations from the forecasting exercise or economics exercise, what is the corresponding injection at bus number 10? If one has to find what is S10, then injection at bus 10 is essentially S10G minus S10D. What is the direction of this flow of injection? The direction of flow of this injection is from the bus into the network. What we are actually interested is to find what should be the current in line number 9 so that this corresponding current, which is responsible for injection power, which is as mentioned here, at bus number 10 is satisfied. So rather than going by the usual convention of injection, what we would do is, since the bus number 10 usually is a load bus, so we'll make our load as the primary concern and generation as the secondary concern. In that case, the injection would change from S10 to minus S10, and then we would have this as the expression for minus S10. Minus S10 is the power which is flowing from the network to bus 10, so that the difference between demand and generation is met. If this is the injection, then this should also be equal to whatever voltage has been chosen at bus number 10 multiplied by the corresponding injection at bus number 10 with a conjugate. So with this reasoning, if I know that, okay, I have started my voltage values from an initial start or a flat start, then using this expression, I can find the current at bus number 10, which is responsible for satisfaction of demand minus generation at bus number 10. If this current exists, then there is only one path for this current to flow, which is through line number 9, branch number 9. And once I know branch number 9 current, then I can repeat the same thing for current required at bus number 9. So at bus number 9, the way I derived for bus number 10, the same expression is written for bus number 9. Bus number 9 has only one current path for the current to flow, which is branch number 8, and hence if I know what are the currents at branch number 8 and branch number 9, I can add them up along with the injection at bus number 6, which is evaluated based on the injections of bus 9 and 10, and I am then able to find what is the current in branch number 7. This same process is repeated for bus 7, 8, 5, 4, 3, 2, till I reach the branch current at line number 1. So similar expressions have been written for other line currents, and till I reach branch number 1 current, this completes one backward phase. When I am finding these currents in the backward phase, then I have assumed my voltages to be the initial choice voltage or the flat start voltage. Once I know these currents, now it's time to do the forward phase where the voltages are now updated. So V1, since it is the source bus or the substation bus, its voltage phasor will not change, but depending on the branch current that has been obtained, the voltage at bus number 2 is updated. Once bus number 2 voltage is updated, the next downstream voltages are bus 3 and 4, so the same are updated again here, and this process continues till I reach the last end bus voltages, which are 7, 8, 9 and 10. And that's how the voltages get updated. You may wonder that, sir, why the currents would lead to update of voltage. The reason why the currents would lead to voltage updates is that these currents have been obtained based on voltage values V0, which are not the true voltages. When you re-evaluate these voltages based on KVL application, so essentially if I were to say what is backward flow, backward method is basically KCL application, whereas forward phase or forward method is KVL application. By doing recursive or iterative backward forward method, we are trying to ensure that KCL and KVL are applied or true for the distribution network power flow, which essentially is also done inherently in the transmission network power flow methods. And that's the reason why voltages would get updated, because when we are doing backward method, we are ensuring KCL is being held true, but KVL check is never ever made. In forward method, we are ensuring that KVL is made true, but then in the next backward method, KCL has to be made true, which is not checked in the forward method. So in one phase of backward forward, we are trying to ensure either KCL or KVL, and when this repeats over a few set of iterations or recursions, then convergence automatically happens, meaning that KCL, KVL both become true. For a network to have currents and voltages, Kirchhoff's law, both the Kirchhoff's law have to be true, which is the basis for all circuit analysis. So similarly, we can find backward current in the next iteration or recursion, and similarly we can find second forward voltage, and this repeats or continues till the convergence is reached. The expressions that you see here are, as I mentioned, for the single phase sample distribution fader. If the same were to be written for one line section in a three-phase network, then this same current I10, which is the injection current at bus number 10, gets blown up as a 3x1 matrix, which is phase A, phase B, phase C currents. The injections are also 3x1 matrices, and when we write the voltage updates, the transmission line, the three-phase distribution line model will have 3x3 admittance or impedance matrix, which are basically the, I won't say impedance matrix, but these are line elements, three-phase line elements based on the nominal pi model. Diagonal terms are the self impedances, the off-diagonal terms are the mutual impedances, which is often applicable for distribution network. Transmission systems, the mutual coupling is not so high, but for low voltages, mutual coupling can exist. And hence, voltage update at bus number 2 for phase A is also dependent on current in line 1 in phase B as well as current in phase C of line 1, along with the current in phase A of line 1. So essentially, the single equations becomes three equations. Every single equation in single phase becomes three equations in the three-phase network. So to end my discussion on backward-forward method, I have taken this different example. I have intently chosen a radial distribution network with 3 buses. The impedance of the lines between bus 1, 2, between line at buses 1 and 2 and line between buses 2 and 3, it's having an impedance of Z with high resistance of 0.2 per unit and a very low reactance of 0.005 per unit. The loads at bus 2 and bus 3, they are P plus J.5 P each. Bus 1 is a substation bus which is represented by this fictitious analogous generator or AC oscillator, and we would try to do or find voltages of buses 2 and 3, because bus 1 voltage is a substation bus, so we have chosen it to be 1 at an angle 0 per unit. For 2 cases where the load is this number and the next case is the P value is this number. It's hardly a difference of 2 to the power 10 to the power minus 8 PU, but these 2 cases will clearly showcase the reason why Newton-Raphson method may or may not work, while backward-forward method or sweep method will still work. The word sweep here is coming also because of the fact that we are traversing or sweeping from lower end buses to upper end buses and then sweeping forward from the upper end bus voltages to lower end bus voltages. So at this P value, the first value, if we were to do Newton-Raphson power flow, with the polar version in consideration, the process remains the same. Both P bus 3 and bus 2 are PQ buses. Bus 1 acts as the angle reference bus or slack bus. There are no PV buses. If we do Newton-Raphson power flow, then it converges in 35 iterations. I think I have used a tolerance of 10 to the power minus 4 per unit for this case. And these are my voltage phasors. Now, this high number of iteration itself is an indication that Newton-Raphson is having a hard time getting the solution of voltages for this 3-bus simple radial single phase distribution network. The reason is that the Jacobian is highly sparsed. In the backward-forward method, we start with flat start of voltages, do the first backward sweep, find the current at I bus number 3, use that current to find line current 2, 3, find the injection current at bus 2, and then eventually find the current at I12 in the initial phase. This completes the backward sweep. In the forward sweep, using the line currents and the impedances, the voltages are updated, which is essentially the reason why this voltage is not same as the voltage that we obtain here. And this continues. In the meantime, we also find the corresponding mismatch vector. You can apply convergence on f of x. F of x is essentially the same f of x that was the set of injections at different buses in Newton-Raphson technique. The expressions for the corresponding injections at bus 2, bus 3. So, the first equation is injection at bus number 2. The second equation is injection at bus number 3. So, it is P2 plus P, P3 plus P. The P is sitting here. P2 is the expression that is present inside this square bracket, and similarly here we have Q2 plus 0.5 P, because load at every bus is half, reactive load at every bus is half of real load, and this pertains to Q3 plus 0.5 P, where Q3 is the term inside this bigger square flower brackets. So, we can also find the f of x check. It has to be essentially 0 at steady state, and these voltages that we obtain, they have to satisfy these equations. So, if the same is done for one iteration of backward forward method, then this is the value of f of x, which after 20 recursions becomes less than the tolerance that was chosen. So, tolerance in this case is I think 10 power minus 3. The same would be the case in Newton-Raphson technique also. With 10 power minus 3 tolerance, the iterations are 35, whereas in backward forward method, it converges in 20 recursions with tolerance of 10 power minus 3. And if the iterations are increased, then after 220 recursions, the absolute mismatch value of f of x further goes down. So, either of the cases, if we now find the voltages, then these voltages are very much the same or similar to what we obtained in Newton-Raphson technique as shown in slide number 10. These numbers in polar versions are same or similar to the numbers that we saw here. The angles are in radians and not degrees. Now, if we increase the load, so essentially in forward backward method, there is no factorization involved, and hence it is highly efficient. Even if 220 recursions are to be obtained, the time required is very, very small. Now, if the load is marginally increased, 0 becomes 2 as I sort of wrote here, then f of x, Newton-Raphson technique keeps on iterating, and maximum absolute value of f of x never goes down below 10 to the power minus 6. On the other hand, backward forward method with this as the maximum absolute value converges into 20 recursions, and the voltage phasors are still being obtained. The backward forward method is still able to give the solution when Newton-Raphson method is failing. This is clearly a case or example how conventional transmission network power flow techniques may not work for distribution networks. In fact, what is so specific that is happening at this particular load, the radial distribution network is reaching a point closer to voltage unstable or unstable operating condition, where voltages are so low, still the network is able to operate. If at all it is able to operate, it will still be able to operate. Operation is not the main point. Point is that will we be able to find the solution from the NR method? Absolutely no, because the load values or voltage values are getting closer to their voltage instability operation, which we will discuss further when we take up the module on voltage instability or stability. With that, I conclude this discussion. The next discussion will be the beginning of our next important module known as contingency analysis or security analysis, in which we will start with basic understanding of what is power system security and what are the typical models that are used for contingency analysis or security analysis. By models, I do not mean that these are mathematical models. No, these are not the mathematical models. Rather, these models pertain to certain process flow models which explain or indicate what control action should be taken so that system security is maintained. We will discuss more on this when we discuss the next discussion. Thank you.